Okay, you've got about 3 minutes to hand in your assignments, and then we're going to start with the lecture. Okay, so today we're going to go through the improper integrals. You should have done the pre-reading. Okay, I spoke about that on the last Thursday. Okay, and then we're going to do a small little chapter on the Laplace transform. Okay, that won't be directly tested, but you will be seeing it next year and in later years. So I'm going to introduce it now so it's not so scary later on. Okay, but for the section on differential equations, if you do want to use the Laplace transform for the bonus marks, I will give that to you. Okay, but you won't be directly tested on it. Okay, but if you want the bonus marks, you can use it if you want. Assignments in the box here, please. Please make sure your assignments are stapled together if you've got more than one page. Yep. Oh, is it there? Yeah. Okay, that's fine. Yeah.
30% for the test, but on students that will showing up after.
Absence.
Yeah.
Okay, I'll double check. That's it. Okay, let's get started. So, improper integrals. This is going to be the last chapter on integration before we look at applications of integration. So after this, we're going to look at the next chapter on finding volumes of 3D shapes. So you're going to be given some equations for some 3D shape. You're going to be asked to sketch the shape, whatever the shape might look like. Then you're going to have to use integration to then find the volume of the shape. Okay, so that's the first big section on applications. Then the next section for this semester will be on finding the moment of inertia. So you would have heard that in physics, moment of inertia. We're going to be doing that here for 2D shapes that are being rotated, rods, like metal rods that are going to be rotated, and we're going to look at the moment of inertia for that. Okay, that will be a big section later on if you're going into mechanical engineering. Okay, moments of inertia tensor, that's going to be a big section later on. Okay, but for now, we're going to look at improper integrals, and these are in two types. So we've got type 1, which is integral, but where the bounds are infinite. So you go from like a to infinity, or minus infinity to b, or minus infinity to infinity. Whenever there's some infinity with the bounds, we call that an improper integral. Okay, that's going to be type 1. And then type 2 is if the function is discontinuous, right? Like 1 over x, there's the asymptote there, or 1 over x squared or something like that. There's that asymptote. Okay, whenever you have an integral with some sort of asymptote, that's going to be a type 2 improper integral, and we're going to look at how to deal with that. Please make sure you have all of your limit stuff from what we did last year, right? Limit laws and L'Hopital's rule. Okay, that's going to be important. So if you don't know that, make a little note on the side. Please go through that before you look at the tutorials. Okay, limit laws and L'Hopital's rule. Okay, you'll need that for the tutorials. Okay, so type 1. Okay, this is going to be where there's some sort of infinity in the interval. Right from a to b, there's some infinity there. Okay, so there are three different cases you can think of. We can either have the integral from a to infinity, f of x dx. So a, that's some finite value, so like starting from 1, but then we go all the way to infinity, whatever that means. We'll have a look at that. We can also have the integral from minus infinity to b, f of x dx. So here, instead of going to infinity in the positive direction, we start at minus infinity, whatever that means, we'll get to that, and then we go up to b, where b is finite, like 2 or something. Okay, and then the third case is like a combination of the two. That is where we have the integral from minus infinity to plus infinity, f of x dx. So it's a mixture of this first one where the top is infinite and the second one where the bottom is infinite. Okay, that one's a little bit trickier than the first two, but we'll have a look at some examples. Okay, so example number 1. We have the integral from 1 to infinity of 1 over x squared dx. Now, if this was just a normal integral from like 1 to 2, for example, you would have the antiderivative evaluated at b minus the antiderivative evaluated at 1. But here, you can't evaluate something at infinity. That doesn't make sense. You can't substitute infinity into a function. So instead of integrating from 1 to infinity, we're going to write this as the integral from 1 to t, or some other variable, whatever you want to call that, 1 over x squared dx. And then after doing the integral, we then take the limit as t goes to infinity. Limit t goes to infinity. Okay, t, you can call it whatever you want. Okay, I'm just calling it t. Okay. So the idea is forget about this infinity in the top here. Do the integral as if it was a normal, definite integral. And then only after we then take the limits. Okay. That avoids this problem of substituting infinity. So instead of substituting infinity like you would think over here, instead we take the limit to infinity. Okay, we know how to take limits. And again, please remember limit laws, L'Hopital's rule, all of that stuff will come up, okay, eventually. So we ignore the limits. So we just write limit t goes to infinity. And then we just do this as a normal integral. Forget the infinity. So we got 1 over x squared. That's x to the minus 2 plus 1 divide. So that's going to be minus 1 over x from 1 to t. So this now becomes the limit as t goes to infinity, minus 1 over t, minus, so there'll be a plus, so a plus 1. Okay, so once the integration is done, then it just becomes a limit problem, right? Exactly what we did last year, right? Just a normal limit problem. So here t is going to infinity, 1 over t, that's going to go to 0, and we're just left with 1. So here this goes away to 0, and here this is just 1. So notice we have an infinite integral. It's from 1 all the way to infinity, but the area under this curve is just 1. Okay. So if we had to draw a picture of this, it will be something like this. Okay, so here we have 1 over x squared from x equals 1 to infinity. So that full area, even though the x part is infinite, the area is still 1. Okay, so it's very weird, but we'll see this quite a few times. Okay, you can have an infinite graph, right? From 1 to infinity, the graph is infinite, but the area is still finite. Okay, very weird, but we'll see lots of things like this. So here, notice we have an infinite graph, but a finite area. Yeah, and we're going to see weird things like this later on, where we have 3D shapes with a finite volume and an infinite surface area, for example. Yeah, we'll see that later when we do the volumes and surface areas. Okay, but for now, just keep this in mind. The graph can be infinite, but the area can still be finite. Okay, let's have a look at example 2. So we have the integral from minus infinity to infinity 1 over 1 plus x squared dx. So here we have an issue because both of these bounds are infinite. Now we can't call this t and this t because they're going in two different directions. This one's going to plus infinity, this one's going to minus infinity. So instead of having minus t and t, we're going to split this up into two integrals. And each one we can do separately. So this is going to be the integral. This minus infinity part, let's call that a. So this will be some a to, let's say, 0. Okay, just to pick something there. 1 over x squared plus 1 plus the integral from 0 to b. 1 over x squared plus 1 dx. Okay, so we split it up into two parts. So instead of going from minus infinity to infinity, we're going to go from a to 0, like a halfway point, from a to 0. And then the second part will be from 0 to b. If we put those two together, we'd go from a to b. Now, what we want is this a to go to minus infinity. So here we're going to have, for this bottom part, limit a going to minus infinity. And completely separate from that, for the other problem, we're going to have b going to infinity. So this one problem from minus infinity to infinity, we split into two problems with two limits. Yeah. So the second one here, this b, we're going to have the limit as b goes to infinity. Okay, so one double infinite integral is converted to two single infinite integrals. So the infinity is just on one of the bounds. Okay, let's have a look at them separately. So let's do the pink one. So we're going to have the limit as a goes to minus infinity of the integral from a to 0, 1 over 1 plus x squared dx. And again, we're going to forget the limit. We're going to treat it just like a normal definite integral, solve the definite integral, and then do the limit. Okay, limit comes at the end. Okay, so this is going to be the limit as a goes to minus infinity. This one we can do right away. There's no need for any u substitution or anything like that. This is just, what's that going to be? Arctan, yeah. So that will be tan inverse x from a to 0. Again, all of this integration stuff, we're forgetting the limit is even there. Only afterwards we then do the limit. So this is going to be the limit as a goes to minus infinity, tan inverse of 0 minus tan inverse of a. Again, not even interested in the limits. We're just simplifying the definite integral. Okay, now tan inverse of 0 is 0, right? Tan of 0 is 0, so tan inverse of 0 is also 0. So that goes away. So we end up with the limit as a goes to minus infinity of minus tan inverse of a. Okay, now either you just know what this is, or you can do a little sketch on the side. Let's do a little sketch. So tan inverse is going to look something like that. Okay, so instead of tan looking like this, right? Tan looks like that. Tan inverse, you just flip it over, right? Inverse, you just flip it over. So instead of this being minus pi over 2 to pi over 2, we now have that for the y values. So this will be minus pi over 2 to pi over 2. So tan x, tan inverse x. Right, you just flip it over for the inverse. So when a goes to minus infinity, we're going to get minus pi over 2. But we got another minus here, so it will be minus pi over 2, so pi over 2. Okay, so that's the first half of the problem. We did the pink integral. Okay, this first one. Let's have a look at the blue integral. And then we just add the results up. So the blue one, this is going to be the integral from 0 to infinity, 1 over 1 plus x squared, 1 plus x squared dx. Okay, we don't want the infinity there, so we replace it with b, and we write this as the limit as b goes to infinity, integral from 0 to b, 1 over 1 plus x squared dx. And now we do exactly the same thing we did for the previous problem. So this is going to be the limit as b goes to infinity. This will be arctan again from 0 to b. Okay, but now they swap. Okay, so it will be limit b goes to infinity, tan inverse b minus tan inverse of 0. Okay, so tan inverse of 0, that comes second now. Same as before, tan of 0 is 0, so tan inverse of 0 is also 0. So that goes away. And then tan inverse of b, when b goes to infinity, we just go back to our picture here. So that's tan inverse. When b goes to infinity, we end up at pi over 2. So this will be pi over 2. So the pink one was pi over 2. The blue one was pi over 2. So the total one is just the sum. So it will be pi. So we have the integral from minus infinity to infinity, 1 over 1 plus x squared dx, will be pi over 2 from the first one, pi over 2 from the second one. So that's just pi. Okay, so remember for these ones with the double infinity here, you're going to have to split it up into 2 problems and then add the results at the end. Okay, in this case, the 2 results were the same, but they might not be. Okay, so check both of them, and then at the end, add it together. Yes. No plus c. All of these are definite. Yeah. For all of the improper integrals, they're all definite integrals, so it's always going to be some number. There's no plus c. Yeah, even for the Laplace transform we're looking at later, it's all definite integrals. Yeah, the whole section's all definite. Okay, any other questions on this one? All good. Okay, next one. Okay, number 3. Okay, talking needs to stop. Okay, number 3, we have the integral from 0 to infinity. X e to the minus x dx. Okay, so we got something like this. Now, if we ignore the infinity, we've seen this before with integration by parts. Okay, so just because this is a new section called improper integrals doesn't mean you forget what we did before. Okay, so U substitution, integration by parts, trig substitution, trig integrals, partial fractions, all of it will be here as well. Okay, so again, forget the infinity. Assignments in the box here. Okay, so forget the infinity. We treat it like a normal integral, and we notice we have to do integration by parts. Okay, then right at the end, we take the limit. That's the only new thing we're doing. So here, this is going to be the limit, let's call it b. B goes to infinity, integral from 0 to b, x e to the minus x, e to the minus x dx. Okay, again, ignore the limits. It's just a definite integral, but we have to use integration by parts. Once we're done with all of that, we then take the limit. Okay, so what are we going to have to do here? Well, this is your u dv type problem. So u will be x, dv will be e to the minus x dx, so everything else. Again, we need du, we need v, so du will be dx, v will be minus e to the minus x. Right, you know all of that already. Okay, so this is going to end up being equal to the limit as b goes to infinity, uv, so that will be minus x e to the minus x from 0 to b. Again, no infinities anywhere there. Limit is done at the end. Okay, so we're still going from 0 to b. Then it's going to be minus the integral from 0 to b, v du, so that comes with the minus there, minus e to the minus x dx. Okay, again, everything on the right-hand side of the limit, it's just integration by parts. Okay, nothing new. So this is going to be the limit as b goes to infinity. Let's expand this out here. So this at b will be minus b e to the minus b. And then at 0, well, we've got an x times that, so that's going to go away. Okay, minus and a minus, that's going to be a plus. Integral from 0 to b, e to the minus x dx. Yeah. Now we just need to do this integral, and then we've got everything in terms of b, and then we take the limit. So this will be the limit, b goes to infinity, minus b, e to the minus b, plus, and then we're going to have a minus e to the minus x, like before, from 0 to b. Okay, substitute, and we're going to end up with the limit as b goes to infinity, minus b, e to the minus b. Then we're going to have a minus from there, e to the minus b, and then a minus minus, so a plus 1. Okay, now all the integration is done, and now it becomes a first-year limit problem. Okay, so all of the stuff before, integration, from now on, limit question. Okay, e to the minus b, when b goes to infinity, that's going to be 0, that's easy. The 1, unaffected. This first one, that's L'Hopital's rule. Okay, so we need to do that on the side. Let's make a little star here, and we do that over here. So this is L'Hopital's rule. Okay, if you forgot L'Hopital's rule, please remind yourself very quickly right before you do the tutorial problems. Okay, when we're taking these limits, there's going to be lots of L'Hopital's rule going on. Okay, so please make sure you remind yourself of that. Okay, so what do we want here? We want the limits as b goes to infinity. Let's leave out the minus. We don't have to worry about that. So let's just take b e to the minus b. Okay, the minus we can take outside of the limit. So this is going to be the limit as b goes to infinity. E to the minus b, we can put that in the bottom. So that will be b over e to the b. Okay, the top goes to infinity, the bottom goes to infinity. Indeterminate form, we can use L'Hopital's rule. So this is going to be the limit as b goes to infinity of 1 over e to the b. Now when b goes to infinity, the bottom goes to infinity, so the fraction goes to 0. Okay, so that's all the stuff in pink is for that first bit there. So this is going to be equal to 0 because of the L'Hopital's rule we did on the side, minus another 0 from the exponential, plus 1. There we get 1. Okay. Some homework. Yeah, I don't know why there's talking. What are you talking about? You got a question?
Yeah, I was asking if
Where did?
yeah, B from the divide.
So you forgot L'Hopital's rule. Okay. Maybe tomorrow we can go through L'Hopital's rule. But remember, if the top goes to infinity, the bottom goes to infinity, the limit is the same as if we did the derivative of the top and the bottom. So over here, we've got f of x over g of x. Over here, we've got f prime of x over g prime of x. Right, that's L'Hopital's rule. Yeah, we can go through it a bit tomorrow, but I can't reteach everything. We can do a few examples, but please make sure you do go over that. Okay. Okay. Careful if you're asking your partners, about questions, they might give you wrong answers. I'm not saying you don't know it, but just in case. Okay, whatever I say, you can take as 100% true. Everyone else, they might be lying to you. Okay, number 1. So some homework problems to try. So we've got the integral from 1 to infinity, 1 over x to the p dx. This is also in the tutorial, okay, but you can try it out now. So what we want is to find the values of p for which this converges. So it gives you some finite value, and which values of p makes this infinite. So find the values of p for which the integral converges. Okay, so converges, you just get some finite value like 1 or 2 or something like that, or diverges. So if it diverges, it means when you take the limit, you get plus or minus infinity. Okay, so there's some values of p where you get a finite value. There's other values of p where it becomes infinite. What are these values? Okay, number 2, interesting one. Prove that the integral from 0 to infinity, x to the n e to the minus x dx is equal to n factorial. Okay, so we did one example here. If we go back here, this one over here was x to the 1. Okay, now you can do the same thing for x to the 2. You'll end up with 2 factorial. If that was 3 in the top there, you'd end up with 3 factorial. For any n in the top there, you end up with n factorial. So try to prove that. I'll give you a hint. Use integration by parts. Right, very similar to what we did for the x e to the minus x. We did integration by parts. Do the same thing, but now your u will be x to the n instead of just x. Okay, so try that out. Okay, any questions on these examples? Okay, so the whole idea for all of these, whatever is infinite, so like your a is infinite or your b is infinite, replace it with some variable like b for the top part. You do the integral as normal with the variable there, and then right at the end, you take the limit. Okay. And please remember your limit laws and your L'Hopital's rule and all of that. Okay, so that's the main idea, is this part here. So infinity at the top becomes a b, and then the limit. Okay, you do that for all the problems, you'll be fine. Any questions? All good. Okay, so that was the type 1 improper integral. And then type 2 is when there's not an infinity in the bounds, but there's a discontinuity with the function. Right, some asymptote. So type 2. Discontinuous functions. Okay. These ones are very dangerous, okay, because they look just like a normal definite integral. But if you miss the fact that it's improper, you get the whole thing wrong. Okay, so we'll look at the first example in a bit, but it looks very, very similar to like a u substitution we did right at the beginning. Okay, you know, with the bounds, with the u substitution. It looks very, very similar to that, but it's improper. If you don't treat it like an improper integral, you're going to end up with infinity minus infinity, and it's just going to be very bad. Okay, so please make a big note on this one. Be very careful with these. It looks very simple. It looks like what we've done before, but you have to treat them differently. And the problem is, with the June test, all of the integral questions are mixed. Question number 1 could be a u substitution like we did in week 1. Question number 2 could be a u substitution, but improper. If you don't know the difference, you're getting 0 out of 5. Okay, so please be very, very careful with these. Okay, so this is the integral from a to b, f of x dx. Okay, it looks very, very simple. However, there's a discontinuity somewhere from a to b. There is a discontinuity at x. Okay, somewhere between a and b. There might be one, there might be two, but there's some discontinuity. Okay, I think for most of the examples, there's only one discontinuity you need to worry about. Maybe there's two. Okay, you would need to check that. Okay, so what does this look like? Okay, well, let's look at the three simple cases. So maybe the discontinuity is at A, but there's some asymptote at A. So we've got something like this, where there's an asymptote at A, and at B, it's fine. So it looks like this. Okay, and we want to find this area here. So B, that's perfectly fine. No issues there. But at A, right, we've got an asymptote. That's going to be an issue. We need to deal with that. Or the asymptote could be at B. So you might have something like this. So A, B, we've got something like this here. So A is fine. There's no issue there. But at B, there's the asymptote. Okay, that's going to be a problem. Or the asymptote could be somewhere in between the two. So you could have something like this. These ones here are also very dangerous. Okay, it's hard to tell just by looking at the function if there's an asymptote somewhere in the middle. Asymptotes at the endpoints you can check just by substituting the bounds, but finding one in the middle, you might miss it. Okay, so here again, we want to find this area here. Okay, and there's some problem in the middle there. Or there might be a case where there's two asymptotes in the middle. So it could be something like this. Something like that. So A is fine, B is fine, but then there's two asymptotes in between A and B. Could be something like that. Okay, so you need to look out for these different cases. Okay, so let's have a look at an example, and then I'll show you how to spot the problems. So number one, we have the integral from 2 to 5, 1 over root x minus 2. Okay, now this looks like something we've done before, right? You've got a root in the bottom, so, you could just write this as x minus 2 to the minus a half. Add half, divide, go on. It looks very innocent. But there's a problem here. Okay, let's have a look at the bounds. If we substitute 5 into the function, we get 1 over root 5 minus 2. It's 1 over root 3. That's fine. No issues with that. Let's look at 2. What does this function look like at 2? Well, we have 1 over root 2 minus 2. That's 1 over 0. There's a problem. So here we have a big problem at 2. There's an asymptote at 2. We need to deal with that. So you can't just integrate this directly and substitute the bounds, because at this bounds, there's an asymptote. How are you going to substitute a value there? So just as a picture, what this looks like is something like this. So at x equals 2, there's an asymptote to the function. And then at x equals 5, there's no problem there. And what we want is this area over here. Now, this can go two different ways, right? We've got an asymptote, which means the function goes to infinity, right? Asymptote means the function goes to infinity. So since the function goes to infinity, this area could also go to infinity, right? If the function goes to infinity, the area underneath the function could also go to infinity. That's one case. Or this might be finite, like we had in this example here. If we go here, in this case, the x part, right, goes to infinity. It's an infinite graph, but the area is still finite. So that might be a possibility. We need to be careful. So x equals 2, that's the problem point. So we're going to remove the problem and then take a limit. So this is going to be equal to the limit as a goes to 2 plus y2 plus. Well, if we look back here, on the interval is from 2 to 5. We're not interested in the interval below 2. We're interested in the interval above 2. So when we take the limit, we need to be very careful and write it as the limit as x goes to 2 plus, not 2. That is wrong. Okay, the limit is 2 plus because we're on the inside of the interval. Okay, if you forgot your limits, left and right limits, okay, again, please go over that. Okay, if you write limit x goes to 2 plus 0. Okay, so a goes to 2 plus. This is going to be the integral from a to 5, 1 over root. Everything else stays the same. So x minus 2, that's all the same there. Okay. And again, triple emphasis. This is a goes to 2 plus. If you write the limit a goes to 2, it's wrong. Everything's wrong. You get 0 out of 5. Okay. And you'll see why it goes wrong in a bit. It's not funny. It's wrong. Okay. And we'll see later when we take the limit, if we have the limit as a goes to 2, the limit is undefined. If you take the limit as a goes to 2 plus, then the limit is defined and we can substitute. Okay. As before, we ignore the limits. We do the integral as normal. Okay, treats it like a normal definite integral. And then at the end, we take the limit. So this is going to be the limit. A goes to 2 plus. Integral from a to 5. X minus 2 to the minus a half. Okay, you can leave out these in between steps if you know it already. Okay, but for the rest of you, we're going to write it as something to the minus a half. Now it's just an exponent. We add 1, divide. So adding 1 makes it a half. Dividing is timesing by 2. So this is going to be the limit as a goes to 2 plus of 2x minus 2 to the half from a to 5. Again, we ignore the limits. Forget about that. We do the substitution, and then at the end, we take the limit. So this is going to be the limit as a goes to 2 plus. This will be 2 roots. We substitute 5, so 5 minus 2. Minus 2 roots a minus 2. Okay, so we're just substituting. 5 minus 2, we can simplify that. So this is going to be the limit as a goes to 2 plus 2 root 3 minus 2 root a minus 2. And this is where this 2 plus comes in. Over here. So remember from last year, left and right limits. A goes to 2 plus means that a is always greater than 2. If this was the limit as a goes to 2, it means we're considering numbers greater than 2 and less than 2. Okay, but this is a goes to 2 plus, so a is always greater than 2. Let's look at the roots over here. We've got the root of a minus 2. And we know from the plus that a is greater than 2, which means a minus 2 is positive. And we can take the root of a positive. If we wrote a goes to 2, that means we're considering values that are less than 2 as well. What happens if we have a minus 2, but a is less than 2? What happens to a minus 2? A minus 2 becomes negative. Can we take the square root of a negative? No. So the limit is undefined if we take a goes to 2. So if you write limit a goes to 2, this limit is undefined and you don't get an answer. But if you write this as limit a goes to 2 plus, then that just becomes 0. Everything's fine. Okay. So please be very careful with how you take these limits. Okay, but a goes to 2 plus, a is greater than 2, so the root there is positive, everything's fine. This goes to 0. Okay, if you did it the other way, you would get everything wrong because you would have to write does not exist. Well, it does exist. It's 2 root 3. So this is 2 root 3. And again, be very careful with how you take these limits. Okay, so just some warning over there. This limit over here is needed for that root over there. Okay. Any questions on this one? You're fine with that. Okay. Number 2. Okay, we have the integral from 0 to pi over 2 sec x dx. Okay. Now again, this looks like something we've seen before. The integral of sec, we've done that 50 times already. Going from 0 to pi over 2, we just substitute. But there's a problem. Okay. The sec over here is an asymptote at pi over 2. So remember cos, right, 1 over sec. Cos looks like this. That's at 0. This is at pi over 2. So everything's fine for cos. Cos of 0 is 0. Cos of 0 is 1. Cos of pi over 2 is 0. That's perfectly fine. But what about sec? Sec is going to look like this because it's going to be 1 over cos. So here, this is at 0. So here we have 1. This is pi over 2. This goes off to infinity. Right? Because we're dividing by 0. Because 1 over cos pi over 2, it's 1 over 0. That goes to infinity. So here we have a problem. Now, if you didn't know that there was an asymptote there, you would treat this like a normal integral and get everything wrong, right? Because of that asymptote problem. So just because it looks like a normal trig integral we've done before, you need to be careful. Check the bounds. Okay. So from now on, whatever integral you're given, check the bounds. Okay. Again, for class test 2, the June test, and the exam, integration is mixed. Question 1 will be something like this, where there's an asymptote. Question 2 will be something like this, which is just a trig integral we've done before, no asymptotes. I'm not going to tell you which one's which. You need to figure that out for yourself. Okay, so we know that there's an asymptote at pi over 2, so we need to be careful. So this is going to be equal to the limit. Let's call it b for the top part. B goes to pi over 2, integral from 0 to b, sec x dx. Now we ignore the limit and then just treat it like a normal integral. Okay, integral of sec, we've done it many, many times now. So this is going to be the limit. B goes to pi over 2. We should be careful with that. It should be pi over 2 minus. Let's just fix that here. Pi over 2 minus. Okay, right. Spend 5 minutes telling you to be careful for this, and then I'll make the mistake. You see how easy it is to make a mistake there. Okay, again, this plus and minus, it is very important. I did forget that here. This should be pi over 2 minus, because look at the bounds here. It's from 0 to pi over 2. So this is 0 less than x less than pi over 2. X is smaller than pi over 2. So we need to have pi over 2 minus. And again, we'll see when we take the limits, that will be important. Okay, please remember, put the minus there that I forgot. Okay, again, very easy to forget that. I just forgot it now. Now, integral of sec, again, we've done it so many times. That's the natural log of sec x plus tan x. right? We've seen that many times now. 0 to b, that stays the same. And then we substitute as normal. So this is going to be the limit as b goes to pi over 2 minus the natural log. We're going to substitute b, so just do it as normal. So this will be sec b plus tan b minus the natural log sec 0 tan 0. Okay, we can do some simplifying here. Tan of 0 is 0. That goes away. Sec of 0, that's going to be 1. The natural log of 1 is 0, so all of this goes away. Okay, so we only have to deal with this limit over here. Okay, now what happens to sec and tan when b goes to pi over 2 minus? Something's going to happen there. Let's draw a little picture again. So sec, it's going to look something like this. Okay, so when b goes to pi over 2 minus, sec goes up to infinity. So this will be plus infinity. Okay, so that's what happens to sec. What happens to tan? So tan looks like this, right? With that asymptote at pi over 2. Now, this is where it becomes important. Pi over 2 minus. Which side of the asymptotes are we on? If we are on the right side of the asymptote, the answer is minus infinity. If we are on the other side of the asymptote, the left-hand side, then the answer is plus infinity, right? So it makes a difference whether you go pi over 2 minus or pi over 2. So pi over 2 minus, we're on this left-hand side, it's going to go to plus infinity. If you were on the other side, you would end up with infinity minus infinity. That's a whole nother problem. Okay, but the first one, that goes to infinity. The second one, that also goes to infinity. So that whole inside part goes to infinity. Okay, what happens to the natural log when the inside goes to infinity? Does it go to like some value? Does it go to infinity? Does it go to minus infinity? What happens? Goes to infinity. Yeah, if we draw the natural log here, it looks like this. Okay, when x goes to infinity, natural log also goes to infinity. So all of this goes to plus infinity. So it diverges. Yeah. So again, all your limit stuff from before, asymptotes, all of that from last year, please make sure you recap that before you do the tutorials. Okay, so in this case, everything goes to plus infinity, so we can say that the integral diverges. Okay, let's have a look at another one that's a bit more tricky than these. So we have the integral from 0 to 3, 1 over x minus 1 dx. Okay, now let's look at this two different ways. So the first way is you forget what we covered in this lecture, you just try and integrate this. Let's see what we get. So integral of 1 over x minus 1, that's the log, right? Integral of 1 over x. So I'm going to put this in red. This is a warning. So if you do it this way, you're going to get some value. You think it's right, it is completely wrong. Okay, we'll see why now. So this equals to, well, 1 over x minus 1, that's the natural log. So this will be the natural log of x minus 1 from 0 to 3. So this will be the natural log. 3 minus 1. Can you see the red? No. Okay, let's change the color. I think the pink is... Can you see that? Yes? No? Yeah, okay. So this will be the natural log x minus 1 going from 0 to 3. So natural log, absolute value, 3 minus 1, minus natural log, absolute value, 0 minus 1. Okay, 3 minus 1, that's 2, so we have natural log of 2. 0 minus 1, that's minus 1. Take the absolute value, that's 1. Natural log of 1, that's 0. So we get this as an answer. Now we're going to show this is completely wrong. But it looks right. It looks very, very simple. And that answer definitely looks right. There's no problems with our working. But there is a major problem. And that is at x equals 1. Look at the bounds from 0 to 3. It includes x equals 1. What happens at x equals 1? Undefined. There's an asymptote there. So it looks like what we had over here, like this green one. So from 0 to 3 at x equals 1, there's some sort of asymptote going on. And that's going to cause big problems. Okay, so what we want to do is write this as two integrals. So an integral for the left-hand side of the asymptote and an integral for the right-hand side of the asymptote. So we're trying to exclude that asymptote in the middle. So this will be the integral from 0 to 1, just before the asymptote. So that's 1 over x minus 1, plus the integral after the asymptote. So that will be 1 to 3. Right, and that 1 that we have there at the top and the bottom, that is the problem point. That's the asymptote. Right, over there. When this bottom equals 0, we get x equals 1. There's an asymptote. So we're going to split it for the left-hand side of the asymptote, integral number 1. Right-hand side of the asymptote, integral number 2. So let's color code these. Let's say the green one for that one and the gray one for this one. So we're going to do it in 2 parts and then just add the results. So let's do the green one. So here we have the integral from 0 to 1, 1 over x minus 1 dx. And keep in mind, problem at 1. We cannot substitute 1 into this function. Doesn't work. So instead of a 1, we're going to write it as a b and take the limit as x goes to 1. So we're going to write this as the limit b goes to 1 minus, because we are less than 1. We're on the left-hand side of the asymptote. So this is the integral from 0 to b, 1 over x minus 1 dx. Okay, and then for the other one, it will be limit as b goes to 1 plus, because we're on the other side of the asymptote. Okay, let's ignore the limits and just treat it normally. So limit b goes to 1 minus. Okay, we're going to just do it as normal. So that will be the logarithm x minus 1 from 0 to b. So this will be limit as b goes to 1 minus natural log of b minus 1 minus, and if we put in 0, we get natural log of 1. That's 0, so minus 0. Okay, now we need to do the limit. So limit b goes to 1 minus, what happens? On the inside bit there, we're going to end up with a 1 minus 1. That will go to 0. The natural log of 0, that goes to minus infinity. So this ends up being some minus infinity there. Okay, again, natural log looks like that. Okay, it goes down to minus infinity. Okay, so that's the first part. That's our green part, this first one. Now let's look at the gray parts for the second one, and we're going to try add them together. But already we have a problem. So the green one is already minus infinity. That's already a problem. Let's see what the other one's going to be. So the gray one, this was the integral from 1 to 3. So we're looking at this one here. 1 to 3, 1 over x minus 1 dx. And again, 1, that's a problem. Okay, we don't want to substitute 1. We're going to replace this with, let's call it a, and take the limit as a goes to 1. Again, there's a problem here at 1. So this will be the limit as a goes to 1 plus, because we're on the right-hand side of the asymptote. So this will be the integral from a to 3, 1 over x minus 1 dx. That's a, not a 9. So that's a A. Okay. And we just do it as normal, like we did before. Forget the limits, do the integral as normal, and then take the limit at the end. So this is going to be the limit as A goes to 1 plus. Okay, natural log again, just as we did before. X minus 1 from A to 3. Okay, and then the A we're going to take to 1. So this is going to be the limit A goes to 1 plus. Here, we put in the 3. We're going to get the natural log of 2. Minus the natural log of A minus 1. Okay, now the natural log of 2, that's fine. Right, that's what we had at the beginning here. For the pink part, we got that. But it's not just that, because this A minus 1, what happens when A goes to 1? This logarithm over there, that's going to go to minus infinity. So this whole thing will go to plus infinity. Right? Because the log goes to minus infinity, you got a minus in front, so it will be plus infinity. Now, that's the problem that we didn't see in the beginning. In the beginning here, this was the natural log of 2. But when we work it out properly, the first part is minus infinity. The second part is the natural log of 2 plus infinity. Now, if you just add them together, you can say minus infinity plus infinity, that's 0. And then we just get the natural log of 2. But plus infinity minus infinity is not 0, right? It's indeterminate form. So here, if we were to add the two together, so the green bits plus the gray bits, this was going to be plus infinity plus the natural log of 2 minus infinity. But this plus infinity and minus infinity, we cannot just cancel. That does not work. Yeah. So the answer is not the natural log of 2. In this case, it doesn't exist. The integral does not exist. The limit doesn't exist, so the integral does not exist. Yeah, integral does not exist. Now, if you go and Google this at home, you might see this as giving you the answer of natural log of 2 using something called the Lebesgue integral. Ignore all of that. Okay. If you go on YouTube and you Google the stuff, you might see advanced math courses with something called the Lebesgue integral. Ignore all of that, right? That is too advanced for you. You're wasting your time looking at that. Okay. So with these types of improper integrals, if you use the Riemann integral, like we've been doing, last year, this year, integral does not exist. That's the answer. But if you look at something called the Lebesgue integral, it will give you something different. Please do not look at that. That is advanced stuff, right? Don't ignore it. Okay. If you do that in a test, I'm going to mark it wrong, even though technically it's right using that, but not in this course. Okay. Okay, so please, this over here, ignore that. Okay, if you're looking at YouTube videos online or notes online or another textbook, please ignore all of that when you Google improper integrals. Okay. You will see it, ignore it. Okay, next example, number 4. So we have the integral from 0 to 1, natural log of x dx. Okay, and again, this looks very similar to what we did before with integration by parts. In the test, I even gave you a question from 1 to 2, or 2 to 3, or something like that in the class test. I think it was something like that, from 1 to 2, or 2 to 3, or something like that. And you did it very easily. Integration by parts, no problem. Now, we've got the same integral from class test 1, but from 0 to 1. Okay? The one in the class test, no problem. This one is improper Because look at 0. What's the natural log of 0? Goes to minus infinity. There's an asymptote at x equals 0. Right, we have an asymptote. And then just a reminder from the class test, integral from 1 to 2, natural log of dx is perfectly fine. No issues whatsoever for that one. I changed the bound slightly. Now it becomes an improper integral. Again, you can see how very easy it is to miss these things. Okay. So again, please, whatever's given to you, please check if it is improper or not. I will not be telling you if it's improper. You need to figure it out. Okay, that's part of the marking. You figure it out. Okay, so it's improper. There's a problem at 0. We need to take the limit as x goes to 0. At 1, there's no problem. Natural log of 1, that's 0, no issues there. So we're going to write this as the limit as a goes to 0. 0 what? Anyone? You said plus. Okay. Bonus points for you. I just need to get your student number. Okay, 0 plus. Good. What? I heard him say plus. Okay, he got it right. He gets points for being right. That's how tests work. So we have the integral from a to 1, natural log of x, dx. Now, if we ignore the limits, this is perfectly fine. Okay, we just do the integral as normal, and then we take the limit. So this is going to be the limit as a goes to 0 plus. Again, ignore the limits. Let's do the integral. We do this by parts. We know the answer already. That's going to be what? Okay, another point. Well done. He got the answer right. He gets the marks. That's how it works. X log x minus x. Now, for the indefinite integral, you would put the plus c. But this is all definite, like we said earlier. So there's no plus c anywhere. We just leave it like this. Okay, from a to 1. So this is going to be the limit as a goes to 0 plus. If we substitute 1, we get 1 times the natural log of 1. That's going to be 0 minus 1. Then we're going to have minus a natural log of a plus a. Right, the minus and the minus will give us a plus there. Now for a natural log of a, what do we have to do there? I don't know who said that first, or somewhere there. Did you say it first? Okay, points for you. Well done. Okay, we have to do L'Hopital's rule, right? Because when a goes to 0, we're going to have 0 times infinity, right? There's L'Hopital's rule there. So let's do that on the side here. So put a little star there, L'Hopital's rule. So we want the limit as a goes to 0 of a natural log of a. Okay, that minus there we can take out of the limits. We don't have to worry about that. Okay, so what we want is some infinity over infinity or 0 over 0, some indeterminate form. Currently, it's 0 times infinity. That's not going to work. So instead, we're going to write this as the limit as a goes to 0 of what? You want some extra marks? How do we convert this to the infinity over infinity or 0 over 0? What do we do? Yep. Put it in the bottom. Yeah, good. Okay, you on? 3. 3 and 1. So yeah, we take it down to the bottom. So this will be natural log of a over 1 over a. Because dividing by a half is timesing by 2. So we're dividing by 1 over a, that's timesing by a. It's the same thing. But now when a goes to 0, the top is infinite and the bottom is also infinite. So we can use L'Hopital's rule now. So this is going to be the limit as a goes to 0. the derivative of the logarithm, that'll be 1 over a, and the bottom will be minus 1 over a squared. Now the a squared we can take to the top, so that will just be an a after cancelling. So this will be minus the limit as a goes to 0 of minus a, but that's just 0. Okay, again, I warned you before with the x e to the minus x problem. Okay, we had to use L'Hopital's rule for that. And again, in this one, we have to use L'Hopital's rule. L'Hopital's rule can and will show up for these problems. You need to know how to apply it. Okay. But that's just going to be 0. The a is going to be 0. We're left with minus 1. Okay, we can do a little sketch of what's going on here. You will not need to do any of these sketches. It's just to show you what's going on. So we got the logarithm. Looks like this. This is at 1. This is at 0. So this area here, okay, the logarithm does go down to minus infinity, but that pink area there is just minus 1. It's like what we saw for the first problem with 1 over x squared. The graph is infinite, but the area is finite. So here the natural log is infinite, but this pink area here is still finite. It's minus 1. Well, the area is 1, but it's below the x-axis, so minus 1. Okay. Any questions on this one? All good. Okay. And again, this could be different, right? We could have the integral of x log x. You know, you'd have to do a different integration by parts, but the idea is the same, right? You replace the asymptote with a or b or t or something like that, do the integral as normal, and then take the limit. Yeah, that's the idea. Okay. Any questions so far? Oh, good. Okay, yeah, please have a look out for these asymptotes. So the natural log, there's the asymptote at 0. 1 over x or 1 over x minus 1, there's the asymptote where the denominator is 0. Please look out for those. The other questions you don't have to worry too much about. Like if you have the integral of e to the x, there's no asymptotes for that, so it's fine. Integral of sine or cos, there's no asymptotes, you're fine. Integral of 1 over x, but now there's a problem. Or integral of the natural log, now there's a problem. Okay, so you don't have to check every single question, but the ones where functions have asymptotes, you have to check. Okay. So just as a little note here, check the questions where the function has an asymptote. Right, only very few functions will have the asymptotes, so you just need to check a few. So for example, the natural log of x, asymptote at 0. 1 over x, asymptote at 0. 1 over x minus a, asymptote at a. Or you could have a rational function, p of x over q of x. You could have a few asymptotes where the bottom is 0. Right, like your partial fractions. Okay, there might be some asymptotes in the bottom. Might have asymptotes there. And that last one there, the partial fractions, you know, I could mix the questions together. I could give you a partial fractions question where the integral is improper. For example, you know, you can mix them up. For example, integral from minus 3 to 3, 1 over x squared minus 1. Something like that. This is a partial fractions question because we can write this inside part as 1 over x plus 1 x minus 1, right? You know, and then you split it up and all of that. But there's two asymptotes. One at x equals 1, another at x equals minus 1. Look at the region here from minus 3 to 3. This includes those two asymptotes. So for this type of problem, maybe you can try it for homework. You would need to do your partial fractions and all of that. But then when you do the final integral, it then becomes improper because of this. Okay. So you can try that one out for homework there. So do your partial fractions on the side, but then you'd have to do something with this. Okay, because there's two asymptotes on this interval. Two asymptotes, x equals plus minus 1. Right, we got that from the splitting up there on the interval. Okay, now you can try that one for homework. Okay, in this case, there's two asymptotes. So you would have one integral for the first asymptote, one for in between the asymptotes, and one after the second asymptote. So something like this. So you would have one for this side, one for this side, one for that side, for each part of that domain. Okay. Any questions on the homework? Oh, good. Okay. And then the last bit for the improper integrals. And then not tomorrow, Wednesday, we're going to look at the Laplace transform. So that will be applications of improper integrals. Okay, and that is the comparison test for improper integrals. Now with this, again, with all the other problems, you get your bonus marks for doing two different ways. Same thing applies for this. Okay. So for the comparison test, we'll have a look at the problems. Some of them you can do two different ways. You get the marks for both, right? Like we had for all the other problems. But we'll see the examples and then you'll see what I mean. So comparison test for improper integrals. So this comes with a little theorem. You've already done the proof for this last year when we did the proofs for definite integrals. So you've done all the working already, but I'll leave the proof for homework. So you can just look at what you did for last year and then apply it to this. Okay, so I won't go through the proof with you. You can try that out for yourself. Okay, so suppose